Good morning. So in this video, what I want to do is look at the mechanism of bromination of an alkene. Now, if you look at the two reactants, a simple ethylene here and a bromine, if you have to ask yourself which is the more reactive species. If you think about the ethylene, we know that ethylene is electron deficient, and so it somehow makes sense for ethylene to be attacked by a base. But the problem is that bromine is a more reactive species. And the key thing on bromine is that bromine-bromine bond is actually very weak. Now, the important thing of having a weak bond is actually not the electrons of the bond, but the fact that a weak single bond means a low-lying antibonding orbital. In other words, it's very easy to break the bond by adding electrons to the antibonding orbital. And that, of course, in this case is what predominates, is that the electrons from the alkene will attack one bromide, actually filling up that antibonding bromine-bromine bond, and then kicking out the other bromide to form a Br-. This, of course, gives us a carbocation. Now, this carbocation looks pretty unstable. Indeed, this one is primary, but it actually has very little independent existence because this bromide has extra lone pairs, and of course, as it forms, it immediately reaches over, and you form the bromonium ion. Now, this bromonium ion, of course, then can be immediately attacked by a Br-, and you form your dibromide. So that's the standard mechanism, and it works very well. In fact, this is a very fast reaction. You can take this bromine, which is, of course, has a nice orange color. You have a solution of an alkene. Now, you wouldn't use ethylene, but say you have hexene. You basically can do a titration where it just immediately, as it reacts, you see the bromine color go away as it's adding to the double bond. It's a very easy reaction, very fast reaction. Now, the bromonium ion is the interesting species because it's this three-membered ring. And of course, it's essentially an isosceles triangle because bromine's bigger than carbon, so the bromine-carbon bonds are longer than the carbon-carbon bonds. So, but it's a nice, stable three-membered ring. Okay, now what happens if we do? This is the reaction that takes place in something like carbon tetrachloride, but what happens in water or an alcohol? So let's say we're doing this in water. Let's pretend here that R is indeed H. So we do this in water. Of course, what happens now is that the water is a better base than the bromide, plus it's also the solvent, so it's in greater concentration. So the bromonium ion is not going to react with the bromide, it's going to react with the water. And you'll get this species down here, which is called a bromohydrin in the case of hydrogen. And of course, that bromohydrin can lose a proton, and you'll form a compound which has got a bromide next to an alcohol, or next to a hydroxyl group. So these are compounds called bromohydrins. They're also very easy to make just by doing this reaction in water. Okay, so let's get rid of the symmetry. So ethylene, the two ends were of course the same. Here we have propene, and they're different. And of course, we're going to have two choices of product. Is the bromide going to go to the methyl carbon, or is it going to go to the CH2? And you can think about this a little bit. You should be able to figure it out because what it's going to do is, again, depend upon that bromonium ion. So what happens here, we're going to form a bromonium ion. But now if we look at that bromonium ion and look at the calculated structure, these structures come from the quantum mechanical calculation. What you'll see here is that it's no longer an isosceles triangle, is that one bond is distinctly shorter than the other. And that's a fairly significant difference, which means this bond is stronger, this bond is weaker. That means that this bond over here will have the lower lying antibonding orbital. And another way of looking at this in terms of resonance is that we can draw two possible resonance structures of this bromonium ion, one with a positive charge on this carbon, one on this one. And of course, the rules of carbocation stability tells you that this resonance structure is essentially a better contributor, and meaning that indeed you should get a triangle which is no longer symmetric. It's not an isosceles triangle anymore. This is the weak bond. And so, of course, the weak bond has a lower lying antibonding orbital, which means the most readily attack is this carbon, because it would rather, when the base comes in, it's going to go for this carbon because it's more acidic. And so it's of course going, when it opens up, then of course you're going to end up with the hydroxyl group on the side of the methyl, because the hydroxyl group is going to come over here. So this what we call regiochemistry is very important. So you have to worry about two things. One is that the incoming base will go for the more substituted center, and it also comes in anti to where the bromide is, because it's going to open from below. So there's both regiochemistry and stereochemistry involved in this reaction. One of the things that's nice to know, the book makes a big deal of this, is that electron-rich alkenes react faster. So if you look at the relative rates down here, ethylene is actually fairly slow. If you have a di-substituted alkene, it's 1,750 times faster. That's a huge difference. So more substituents make the alkene more electron-rich, okay, which means it's a better base. Better base from the more electron alkene will attack the bromine more readily, faster, which means that you go over here to a tetra-substituted one, it's really fast. Which you can take advantage of this in synthesis in principle. So if you had some say complicated hydrocarbon, and you had say a terminal double bond, which would be monosubstituted like this one here, and you had a di-substituted bond elsewhere in the molecule, you could say, well, this one's 17 times faster than that one, and that's good enough for a synthesis. So you could add your bromine, and you could assume that your yield would be very high for adding it to the di-substituted one. So that's something to keep in mind. There's also a steric factor, because if you see here, T-butyl next to the double bond is slower than the N-butyl. Now that's not a huge difference, but it is something to keep in mind. Okay, so let's do an example here. We're going to add the bromine to this methyl cyclohexene. What's the product going to be? So how do you figure this out? Well, again, you're going to form the bromonium ion, of course, and then you have to say, well, where is the alcohol going to attack? Is it going to attack at the methyl or the way? And of course, you know the answer, because again, this bromonium ion is going to be unsymmetrical, because the bond to the carbon with the methyl group is going to be longer, so this is going to be the place of attack, and it's going to have to come from the bottom. So which one is that? Well, if you look at all these have bromines up. Of course, the enantiomer would have bromine down, but bromine is always up. The methoxy has to be on the methyl. Here's the methoxy on the methyl, but it has to be trans to the bromine, so it's D. And of course, these, if you really draw these out as hexanes, these would be the pair of enantiomers. And so the interesting thing is that these things, when they form, essentially it forms in anti-position, but with two substituents, you want them both to be equatorial if possible, so it immediately switch from the axial position to the equatorial. Okay, so let's do another problem. What's this going to get? This looks very much like the last one. We had methyl cyclohexane. Now we have methyl cyclopentene. So we're going to do a bromonium ion addition. But then what is that sodium ethoxide going to do? Is it going to substitute for the bromide? That seems like a reasonable thing to do. You can imagine a substitution reaction, or is it going to do something weird? And of course, I'm setting you up. It's going to do something weird. So let's look at the mechanism. When you look at this here, you have ethoxide. It could do SN2 chemistry and attack the bromide, okay? Or it can do something which is a lot faster, which is just do a proton exchange. You have one alcohol and another, and of course those are going to exchange protons very fast. It'd be at equilibrium, but you very quickly get some of this alkoxide. And this alkoxide can do a reaction which your ethoxide can't, because this one here can do an intramolecular substitution reaction. So this is indeed an SN2 reaction, but it's not an SN2 reaction of the ethoxide. It's an SN2 reaction of this O-, and it just comes over, kicks out the bromide, and we've ended up forming a epoxide. And so this is a good way to make epoxides, different than what we covered before. Do you remember the other way of making epoxides? Where else do epoxides come from? Well, you need a source of oxygen to oxidize that double bond. What's the source of oxygen? Well, you usually use a peracid. And the common one is this metachloroperoxybenzoic acid. These peracids are actually kind of interesting molecules because they just look weird, and they're much more reactive than normal carboxylic acids because of their ability to do oxidations. You make these peracids themselves by starting off with an acid anhydride. So in this case, you take the anhydride of chlorobenzoic acid, metachlorobenzoic acid, and you treat it with hydrogen peroxide. You can imagine the hydrogen peroxide just attacks one carbonyl, forms the peroxy acid, and kicks out the carboxylate of the other one, which then grabs the extra proton. So here you have your peroxybenzoic acid, so the question I want to ask is it stronger or weaker than normal carboxylic acid? This is actually kind of an interesting question. Which of these is a stronger acid? Now, how would you figure this out? Well, this one here, you might argue, well, this one's going to be pretty strong. It's a hydrogen and there's on 2 oxygens. We know there's a big electronegativity effect. But there's a problem. What's the problem over here? Well, why are carboxylic acids stronger acids than alcohols? Well, because of the resonance effect. If you have O- here, of course, you can delocalize it into the carbonyl. What if you have an O- over here? Well, you're stuck. You can't delocalize an O- on the hydrogen of the peroxy acid onto the carbonyl. It doesn't work. So if the metachlorobenzoic acid has a pK of 3.8, this one, the peroxy one, is going to be higher. In fact, it's 7.6. Now, the interesting thing, it's not as high as an alcohol. Alcohols are up around 16. And, of course, that's the electronegativity effect of this oxygen. So the first oxygen, it basically acts like it really acts, think of it as peroxy acids as like extra acidic alcohols, if you will. But the key thing is we're not worried about acidity. We're worrying about delivering an oxygen. And the mechanism is just like we did with the bromine. The double bond is going to attack this oxygen because what it really finds is this weak oxygen-oxygen bond is weak. The antibonding orbital is low. So again, it's going to attack the back lobe of the antibonding orbital, kick out the carboxylate, and then form this species here, which again is now, in this case, a secondary carbocation, and that's going to immediately close up, just like the bromonium ion did, and you'll form this protonated epoxide, which the carboxylate will grab the proton from, and you'll go to your epoxide. If you remember, the epoxidation is stereospecific, so when you look at the substituents on an alkene up to 4, their relative positions in the epoxide are going to be the same. So in other words, the oxidant just adds to the top or the bottom. There's no other changes in the molecule. So in this case down here, which one are we going to get? We're going to look down here. What's the difference? So here I have 2 ethyl groups, they're cis. Here I have 2 ethyl groups, they're trans. And of course up here they're trans, so B has got to be the right one. So this is important to remember because you can construct a lot of really complicated molecules using this epoxide technology. You can read about this in the book on page 429. Anyway, epoxidation, just like bromination, is also faster with more electron-rich alkenes. And so again, if you look at this one here, ethylenes again is 1. The tri-substituted one here is 6,500. So again, if you're clever and you have more than one double bond, let's say you have a single substituted double bond and a doubly substituted double bond. Again, there's a big rate difference here. What is it? It's about 20 in this case. So a 20-to-1 ratio is enough for synthesis. So if you want to do a selective epoxidation, you can do that when you have 2 double bonds, but their substituent pattern is considerably different. So that is a look at the